In section 3.6, we're going to finish finding our derivative rules, looking at derivatives of inverse functions. So in this section, we're going to use the chain rule to find the derivatives of inverse functions, such as logarithm functions and inverse trig functions. So let's recall some facts about inverse functions. We call f to the -1 power x, that's f inverse of x, is the inverse function. And if we compose the function and its inverse, so f of f inverse or f inverse of f, those functions kind of cancel each other out and we're left with just x. And I think maybe the best example of this is to think about the cubed root of x cubed. We can clearly think about the cubed root and the cube canceling each other out, and we're left with just x. We can do this with other more complicated functions, such as natural log and e to the x, as those are inverses. So that means that natural log of e to the x is equal to x, and e to the natural log of x is also equal to x. And then we're going to look at inverse trig functions. So that is sine and arc sine. Note that arc sine is another name for sine inverse of x, but I'm not going to use that notation because it's a little bit confusing on what that -1 means. So we're just going to use arc sine instead. So those are inverses. Note that they're only inverses on the special interval -pi/2 to pi/2. Arc sine has a restricted range, but barring that, these are inverses. So sine of arc sine of x is equal to x, and arc sine of sine of x is equal to x. And we're going to use that kind of relationship to build the derivative of the inverse. So here's how that's going to work. To find the derivative of f inverse, we're going to use the fact that f of f inverse of x is equal to x, and we're going to use the chain rule. So we're going to start with the fact that f of f inverse is equal to x, and we are going to take the derivative of both sides of the function with respect to x. The reason we can do that is because we can really do whatever we want to an equation as long as we do it to both sides of the equation equally. In this case, we're going to take the derivative of both sides of the equation, and those should still be equal as the derivative is a well-defined function. So the right-hand side of this is very easy to do. It's the derivative of x, that's just 1. The left-hand side, we need to use the chain rule in order to take care of this. So we have the inside function is f inverse, and the outside function is f of something. So the chain rule says that we should take the derivative of the outside, f prime. We're going to leave the inside alone, f inverse, and we are going to multiply by the derivative of the inside. And note this is all equal to 1 because the derivative of x is equal to 1. And now we actually have an equation where we have what we're looking for, the derivative of f inverse. So now I'm going to solve for that by dividing on both sides f prime of f inverse of x. And this will give us that the derivative of the inverse is equal to 1 over the derivative of the inverse. There is our formula that we can use to kind of find derivatives of log and inverse trig functions. So here's the formula again written out. The derivative of f inverse, if f is a differentiable function, is 1 over f prime of f inverse of x. And I want to make very clear that this formula is not going to be used very often. In fact, it's the most useful to find the formulas of the log and inverse trig functions. So it's good to kind of know it's useful in some circumstances, but it's probably the least useful derivative rule that we kind of have now. And we're really not going to use it past this section other than getting those new formulas. All right, so now let's move on to our derivatives in this section. The derivative of natural log of x is going to be equal to 1 over x. And let's see this done just as we did before. We're going to use the fact that the composition of natural log and its inverse, in this case, e to the natural log of x, is equal to x. And we're going to take the derivative of both sides to find this derivative. So we're going to have to use the chain rule. We have the inside function is natural log, the outside function is e to the x. We're going to take the derivative of the outside, which is just e to the x, leave the inside function alone, and we're going to multiply by the derivative of the inside function, and this should be all equal to 1. So if we divide by e to the natural log of x, we get the derivative of natural log of x is equal to 1 over e to the natural log of x. And then note that we can simplify the e to the natural log of x to write this as just 1 over x. All right, now we have this rule and we are able to use it freely. The derivative of natural log is 1 over x. We can do a very similar thing by finding the derivative of log base a, noting that a to the log base a of x is equal to x, as a to the x is the inverse of log base a. In this case, let's use the formula that the derivative of the inverse is 1 over f prime of the inverse. So to use this formula, we need to know that the function that we're thinking about here is a to the x, and the inverse is log base a of x. So this derivative should be equal to 1 over the derivative of a to the x, which you recall is natural log of a times a to the x. But instead of having x, we're going to replace that with the entire inverse function. And then note that we can simplify the a to the log base of x, and we can write this all as 1 over natural log of a times x. And once again, now we have this rule, and we can just use it freely. All right, we're going to do a similar thing now with inverse trig functions. So here are the derivatives of our inverse trig functions, and note that we're only going to look at arc sine, arc cosine, and arc tangent, as the other three, arc secant, arc cosecant, and arc cotangent, are not very useful and do not show up very often, and really do not show up at all. So we're going to use just these three inverse trig functions, and we're going to have to know these derivatives. And these are probably the hardest derivative rules we're going to do just because they seem very they don't seem like they should be the derivatives of these functions. Why is the derivative of arc sine involve a square root and a 1 minus x squared? And that seems very confusing. And we'll talk maybe about a way that we can remember why these are true, other than just knowing how to find them. To show how this works, though, we're going to use the same kind of method to show why the derivative of arctangent is 1 over 1 plus x squared. And the next video, we'll do the same thing with arc cosine. So arctangent, let's do the same kind of thing where we're going to have the fact that tangent of arctangent of x is going to be equal to x. And we are going to use that fact to find the derivative. So we're going to take the derivative of both sides. The derivative of tangent of arctangent, we need to do the chain rule. Chain rule says that we need to take the derivative of the outside function, that is secant squared. We are going to leave the inside function alone, and we are going to multiply by the derivative of the inside function. So we'll leave the inside function alone, multiply by the derivative of the inside function, and this is all equal to 1 because of the derivative of x. So now here comes our formula, and we could have just jumped to this step right away. The derivative of arctangent of x is equal to 1 over secant squared of arctangent of x. And that's true, it's just not the nicest way that we could write this derivative. But unlike with the log functions, secant squared and arctan don't just cancel out right away. So we can't just immediately simplify this, but we can use the Pythagorean theorem to rewrite this. In this case, we're going to use the Pythagorean theorem that tangent squared plus 1 is equal to secant squared. So I'm going to replace secant squared with tangent squared plus 1 in that expression. And that'll give us 1 over secant squared is going to turn into tangent squared plus 1. I'm going to actually write that as 1 plus tangent squared, just so we can kind of see where it's going to come from. So this is going to be 1 plus tangent squared of arctangent of x. We replace secant squared with 1 plus tangent squared. All right, now we can do a simplification. Now tangent of arctangent is just equal to to x. So we're going to simplify this, and we should get 1 over 1 plus x squared because of the tangent squared. And there is our derivative. The derivatives of arc sine and arc cosine are done in a very similar fashion, just using a different Pythagorean theorem, different version of the Pythagorean theorem. So one more thing is to how can we remember these derivatives? And to me, it all comes from that Pythagorean theorem that we just used, tangent squared plus 1 equals secant squared, or sine squared plus cosine squared equals 1. So first, let's look at sine and arc sine. And we're going to think about the derivative of sine is positive cosine. And if I solve for cosine in the Pythagorean theorem, then I can write this as cosine squared x equals 1 minus sine squared x, or cosine of x is equal to the square root of 1 minus sine squared x. And to me, this is how we can remember what the derivative of arc sine is. Remember that we have the derivative of arc sine is 1 over the square root of 1 minus x squared. And that square root of 1 minus x squared and 1 minus sine squared are awfully similar. So that's how I would remember it, is thinking about the Pythagorean theorem and the derivative of sine. In a similar way, we could do the derivative of arc cosine, noting that the derivative of cosine is negative sine. And if we solve for sine or negative sine in the Pythagorean theorem, we get that sine squared is equal to 1 minus cosine squared. So sine is square root of 1 minus cosine squared. And then one other detail, which is negative sine is equal to negative square root of 1 minus cosine squared. And remember that the derivative of arc cosine is negative 1 over square root of 1 minus x squared. And there is definitely some similarities there. The negative comes from the fact that we're doing the derivative of cosine is negative sine. That's where that comes from. Otherwise, it's kind of the same as arc sine. And then for tangent, we kind of already seen it, but note that the derivative of tangent is secant squared. And we have 1 plus tangent squared equals secant squared. We have this 1 over 1 plus x squared. So here, we don't need to do anything with the square. We're going to say that these terms are similar. It's different than the other two because the derivative of tangent is secant squared instead of just secant itself. So that is one way to sort of remember very quickly the derivatives other than just memorizing them. Arc sine and arc cosine are similar. They differ by a negative. Arc cosine is the negative one because the derivative of cosine is negative sine. And the square root of 1 minus x squared comes from solving for sine or cosine, the Pythagorean theorem. Arc tangent's a little bit different because we have secant squared, but it's the same sort of idea. In the next video, we're going to do a bunch of practice problems using these derivatives, as well as all the other derivative rules we've come up with so far.